All right, so today you're going to be learning about modeling linear and exponential functions, and I use the term learning lightly because you have done all of this before. So learning goals. I can write a function that models a real-world situation. You have to do that for both linear and exponential. Determine if the function represented graphically is linear or exponential, and then use a constructed function to determine additional information in a real-world problem. So some things to remember. If you have a linear function, it has a constant rate of change. So if you have a graph, it will be a line. If you look at it as far as the table goes, the amount is increasing by adding or subtracting the same number every time for your y values. For exponential, things change by a percentage rather than a fixed amount. So that means that you will notice that things are not changing at a fixed rate. Your graph will have a more curvy look to it, okay? Or it could be, like this, either way. And on a graph, you may be multiplying by the same number each time rather than adding or subtracting. So Mike is saving for some new medical gloves, which cost $55 for a case. He's already saved $17. His goal is to have enough money saved in 6 weeks to pay for the gloves. Write an equation that represents how much money he needs to save each week to meet his goal. So for this, we are looking at a few different things. So this is, again, going to be in that y equals mx plus b format, or we could put the y equals on the end. The only thing that's different is here we're not necessarily going to have a y and an x because we actually have a y. We know what the total cost is going to be. The total cost is going to be $55, so that's going to go on one side by itself. Now he already saved 17, so we're going to include that on our left side, and then next we need something with a variable. So it says that he saved enough money in 6 weeks to pay for the gloves, and it says write an equation that shows how much he needs to save each week to meet his goal. So this would be our equation, 6 times x. Now if we wanted, what we could do, and what would be a good way to kind of get into some practice doing this is solve it for x. So once you have it here, what you could do is back this up. Is you could say, well, I'm going to subtract 17 from both sides. Okay, 15 minus 7, that's 8. Let's see, so 38. That sounds about right. So we'd have 6x equals 38. And we divide both sides by 6, which would give you 633. So there we're solving it, but that's technically still an equation. So just x equals 633. But just so you kind of get, like when it says solve for something, that's one way you could do it. But this is lovely as well. We've got our variable and everything in it. All right, next. The species of monkey initially had a population of 12,125 when scientists first began studying it. Since then, the population has increased by 1.2% each year. We want to know how many monkeys there are going to be after 11 years. So remember your setup. A times 1 plus the rate of change raised to the t, or time, or x, however you want to look at it. So A is our initial amount. We started with 12,125. We are increasing, so it's going to be 1 plus, not 1 minus. We are increasing by 1.2%. Remember, 1.2% is the same as writing 0.012 because we take that decimal and we move it over 2 spots always. Okay? And we do know the years. Okay, it's after 11 years. So we go ahead and we put all that in our calculator. I would suggest adding these two numbers first before you raise it to the 11th power, just a suggestion. And you come up with 13,825 monkeys. Next example. We've got a table. This models the number of cubes for figures 1, 2, and 3. And we want to know if this is going to be a linear or exponential function. So the easiest thing to do is to make a table. So we've got figure 1, which has 1 cube, 2, which has 2 cubes, and so on and so forth. And then what we're going to do, if this is our x, and we're going up by 1 each time, right? So what we're going to do is look at our y and see what's going on here. Are we increasing by, if it's linear, we're going to be increasing by the same amount. So this would be plus 1. So this would have to be plus 1, and so would that. You can see that it's not, which kind of tells us it's exponential. But just to be sure, are we multiplying by the same number? To get 2, we'd have to multiply by 2. We're multiplying by 2 each time. So yes, this is exponential. All right, so there are a total of 281 Achieve articles that need to be completed during freshman year, and a student completes 7 Achieve articles per week. What's the function rule that describes this? Simply 7x equals 281. So this is the total amount that we want. We do 7 per, so there's that per right there, week. So this is going to be our variable. How many Achieve articles are left to complete after 12 weeks of school? So 12 weeks. So this is going in for x. 7 times 12 is 84. And we take, because that is how many we've read, we want to know how many are left to complete. So 281 minus 84 gives us 197. So we want to use the function in part A to determine how many weeks it takes for the student to finish their articles if they complete them at a continuous rate, meaning they read the same amount of articles, this 7, every week. So all we have to do is say, well, just solve for x. So if we have 7x equals 281, why isn't my 1 showing that? Whatever. Nothing's showing. Okay, so 7x equals 281. Divide both sides by 7. That's strange. And you will get an answer of about 40.1 weeks. That's a lot of reading. Hopefully you guys are much better about that. Or about 40 weeks. All right, last one. A hoverboard valued at $300 loses 15% of its value each year. Write a function rule that models the value of the hoverboard. Well, right away we should know that this is an exponential function because we're seeing a percentage sign. Okay, so we're going to set it up. Now the reason why I did this, let's see if it'll work. Is this going to work? Nope. Maybe. That's fine now. Here we go. Okay, so remember it's A equals, if I can go back just to take a quick look. Sorry about this. I just want to make sure you know where I got it. So I've got over here A times 1 plus R to the T power. But if it's decreasing, it wouldn't be plus R, it'd be minus R. Okay? So that's why I did minus 0.15. which is the same as 300 times 0.85 to the x. It says find the value of the hoverboard after 5 years. So all we have to do is plug in 5 for our x value, because that's for time, which will give us $133.11. And then how many years will the value of the hoverboard be less than 85? The easiest way to do that is to graph it. The other way that you would do it is to plug in the 85 in for the f of x. The problem with that is it can get a little tricky. So I would recommend just taking your formula that's from part A and graph it and look on the y-axis for when you dip under 85. My suggestion to you. All right, that's all there is for C. If you guys have any questions, so please bring them up in the classroom. And as always, have a lovely